Welcome everybody. Today we're talking about wood shear wall seismic and wind design examples per the 2015 Wood Frame Construction Manual and special design provisions for wind and seismic. So, okay. There we go. Nice. All right. You guys have all seen the description and the learning objectives for this presentation when you signed up, so I'm not going to spend any time on those. We're going to do a series of polls today to keep everybody engaged in the presentation. So here is our first one. This one's the best one because there's no wrong answer. So we'll let Marcy launch this and everybody can see what their profession is.
Absolutely. So go ahead and answer if you are an architect, engineer, code official, or if you're in the fire service somehow, volunteer, professional, however you might be involved in the fire service, or if you're some other profession. And as always, I wait until about 80% or about 35 seconds. So I've got both of those, so I'm going to close. And let's see who we've got here. We've got 78% engineers, 13% code officials, and then just a smattering of the other professions. No matter what profession you are, we are happy that you're here and hope that you find value in today's topic.
Great. All right. Thanks everybody for joining us. So here is an outline of today's presentation, and so I'll be kicking it off and talking about some of the IBC and IRC recognition for these two documents. We'll talk about the background on them and some of the assumptions that are used in the design, and then I'll present some examples for a wind-driven design, and then Michelle's going to take over and she'll present some examples for a seismic controlled design. So the first document we're going to talk about, the first standard, is the WFCM, which is the Wood Frame Construction Manual. This document is referenced in both the 2015 IRC and the IBC. So if you go into the IRC, you'll see it's referenced in section 301.11. So this means that the WFCM can be used regardless of the load limit triggers in the IRC. So you can use it in higher wind regions and things like that. In the IBC, you'll see in section 2301.2 that the WFCM has a reference that tells you to check the requirements of 2309. So in section 2309, it requires that anything designed with the WFCM has to be in risk category 1 or 2, and it also needs to be within the limitations of the WFCM. So this is going to limit our applicability to residential, to multifamily, and some light commercial and retail structures. We'll discuss the applicability limitations of the Wood Frame Construction Manual in a couple different spots today. So this is at the beginning of the document. This is Table 1. So this is going to provide the overall requirements, regardless if you're using the engineered or the prescriptive path for design. So it has limits on the building's geometry, the height, the length, the width. You'll see additional limits on the dead loads, the live loads, and the other gravity loads, the snow load. So for live load, and the floor live load will be limited to 40 pounds per square foot. And then you'll see the ground snow load goes up to 70 pounds per square foot. For lateral loads, we have an allowable wind load for 110 to 195 miles per hour, and we can accommodate with the WFCM exposures B, C, and D. For seismic, you can do anything in a seismic design category A, B, C, or D. Now the IRC does have further has 3 subcategories for seismic design category D. So you'll see those noted as well, D sub 0, 1, and 2. So for non-residential applications, some examples of places you could use the wood frame construction manual. You might have a single-story slab-on-grade structure. The WFCM would be very helpful in an instance like that. So other structures where it might be useful, you would be a commercial or a retail structure for restaurants or small office buildings. And the WFCM can be used to design the lateral components, the wind and the seismic resistance, and it can also be used for gravity loads. So it's a really handy document, and it can save you a lot of time with a lot of the tabulated provisions in the document. So here's a slide that shows the layout of the table contents of the WFCM. So you'll see in Chapter 1, it provides some general information, the scoping, and some definitions. And Chapters 2 and 3 provide parallel paths for design. So Chapter 2 is the engineered design approach, and Chapter 3 is the prescriptive design approach. And you'll see that they both have a very similar layout in terms of connection, floor, wall, and roof designs that are contained within. In terms of where the loads come from for the wood frame construction manual, the 2015 version uses ASCE 710 for the wind and seismic design provisions for lateral loads. It also references ASCE 710 for gravity loads as well, but since we're primarily concerned with shear walls and lateral today, that's what we're focusing on. Now this is the other document we're discussing today. This is the special design provisions for wind and seismic. You may hear me refer to this document as SPDWS. That's just a shorthand notation we have. It's a little shorter than saying special design provisions for wind and seismic. So if you hear me say SPDWS, I mean this document here. So the 2015 SPDWS is referenced in the 2015 IBC. Unlike the wood frame construction manuals, this is purely an engineered document. So it can be used for any structure. It can be used for residential and non-residential, and it is a dual format approach. So you have ASD and LRFD design provisions contained within it. For your shear wall design provisions, we have 3 options. We have the segmented option, the perforated option, or forced transfer around openings. Now, when we're in the wood frame construction manual, I didn't mention this, but we only have 2 options for shear walls in the wood frame construction manual. We have a segmented option or a perforated option in the WFCM. So SPDWS gives us another option for shear wall design. Today's examples, we're only going to focus on segmented and perforated. Forced transfer around openings, those examples can get a little lengthy. We do have other programs on our website. If you're interested in FTAO design, you can check it out on awc.org/education. But so here's a few places where you see the special design provisions for wind and seismic referenced in the 2015 IBC. So you'll see it is in 2305, 06, and 07. I do want to point out that there are some inconsistencies in the IBC with how they reference our documents. So in some places you'll see AF and PA special design provisions for wind and seismic, and in some places you'll see American Wood Council. AF and PA is our old name, so there's just a few spots where they haven't updated it to our new name. So it is the same document. It's still us. It's just how the document is referenced. You'll also see in ASCE 710 that the National Design Specification, or NDS, and the Special Design Provisions for Wind and Seismic are both referenced in Chapter 14. So this contains reference documents and shows the key references for wood systems resisting seismic forces in Chapter 14. So we do have a reference in ASCE 710 as well for the special design provisions for wind and seismic. All right, so next we're going to jump into some background and some assumptions. So this is the segmented shear wall design method that we're going to discuss first. So this assumes that we have full height segments that are sheathed on the wall, and at the end of each of those segments there's a hold down. It doesn't account for any contribution above or below any openings where you might have additional sheeting, such as in these locations here above and below the opening. This method is considered one of the simplest, and it's the most straightforward. And it is included, as we mentioned, in SPDWS as well as in the WFCM. So this is something that you can use in either document. The next method we're going to discuss is the perforated shear wall method. So the perforated method assumes that we have a fully sheathed wall, and it will allow us to have contributions from the sheeting above and below the openings. Additionally, we only have hold downs at the ends of the wall. So we've taken the hold downs where we'd have them at each full height segment, and they're only now at the ends of the walls. Again, this method is also included in both the special design provisions and in the wood frame construction manual. So here's our second poll.
Yes, indeed. So we've got WFCM prescriptive provisions include which of the following? 110 to 195 mile per hour wind loads, exposures B and C, segmented and perforated shear walls, or all of the above. And I've got about 50% have voted. So let's get a few more people in there to vote, and just a few more seconds. All right, I've almost got 80% and 30 seconds, so I'm going to go ahead and close. And let's see, 83% say all of the above, and just a few more the rest are scattered above. So let's see if those 83% were correct.
Yeah, they are. The majority is correct. So the answer is D, all of the above. All right. All right, so now let's jump into talking about some examples. So we're going to start with wind. So we're going to start in the prescriptive examples with the WFCM. So in Table 3, we look at some of the prescriptive design limitations that are for Chapter 3. And these are the building dimensions, the spans, things like that, they're included. But we do also have some additional limitations like we talked about earlier. So for our seismic design categories, we're limited to A through D. Wind speeds 110 to 195 miles per hour for exposures B and C. Now, I know we mentioned earlier that you can use the WFCM for exposure D. However, for exposure D, you need to use the engineered approach, which we're going to discuss next. If you're using the prescriptive approach, we only have tabulated results for exposures B and C. Again, as I mentioned, we have segmented and perforated shear wall design options in both the prescriptive and the engineered chapters in the WFCM, and those other application limits we talked about related to the gravity loads and the size of the structure. So if you go into the WFCM, we have all these tabulated values, and we have a baseline assumption for our shear wall design in Table 317D. So this baseline assumption is that the wall is sheathed on one side. The studs are at 16 inches on center, and it's sheathed on one side with a minimum 3/8 inch wood structural panel. We've got nails attaching it with 6 inches on center spacing at the edges of the panel and 12 inches on center spacing in the field. And then on the inside of the wall, it's assumed that you've got a 1/2 inch of gypsum wallboard attached with 5D cooler nails with a 7-inch edge spacing and a 10-inch field spacing. So there is a footnote in Table 317D that refers you to SPDWS. So I want to show you guys the note from SPDWS that talks about this aspect ratio capacity adjustment. So there are limits, and we're going to look at them several times, these limits on the aspect ratio of the shear wall segments. So where our aspect ratio is greater than 2:1, we have to multiply by 2BS over H. Now this is in 2015, in the 2015 wood frame construction manual, this is something that we don't have to apply to wind designs. It applies in 2015 to seismic designs only. In the 2018 WFCM, it will apply to both wind and seismic designs. But so in my WFCM prescriptive design, you won't see me take the adjustment on these higher aspect ratio panels because of that requirement. When we move to the 2018 WFCM, that aspect ratio adjustment will be taken on all high aspect ratio segments, regardless if it's wind or seismic design. So this is the design example structure that we're going to be working with today. It is a 2-story house. You can see 36 feet long in this dimension. And for each of the examples we're going to work today, we're going to design the first floor shear wall. So at the ends, you can see we've got a 4-foot width of wall at the end between the edge of the window and the end of the wall. And then between the windows, we have a 2.5-foot segment. So for our wind example, we're assuming it's a 130 mile per hour wind zone, exposure B. The wall we're looking at is 36 feet long, and the wall that runs into your plane of your screen would be 30 feet, so that's the wall perpendicular to this one. Our roof pitch is 5 and 12, and we have a top plate to ridge height for our roof of 6.25 feet. As we mentioned, it's a 2-story structure. Our walls are 8 feet high, and we have a door opening that is 6 feet 8 inches high, and our window heights are 4 feet. We talked about that wood structural panel exterior sheathing baseline wall. We're going to use that, and we're going to check the interior walls both with and without the contribution of the gypsum. So for wind design in SPDWS, I believe it's 43332, there's an exception that allows us to combine the capacities for wood structural panel and sheathing wall, but it's for wind design only. So we're going to check it with and without the gypsum, and we're going to neglect the deflection check in this example. So using the prescriptive approach for the segmented shear wall requirements, we go into our table 317A, and this gives us the length requirements for the shear wall. How long do our full height sheathing segments need to be? So we go into our 130 mile per hour column. So our minimum height of full height sheathing on exterior shear walls perpendicular to the building dimensions. So we're designing the 36-foot long wall. So that means we use the building dimension W in this column here. So we need to interpolate between these two cells because our W is equal to 30. So we get a value of 12.3 feet. Now you'll see that we have several footnotes that apply up here. So if we check those footnotes, we'll see that footnote 4 is especially important. It provides an adjustment for the required sheathing lengths based on the wall height and the top plate to ridge heights. So the tabulated values assume that the wall height and the top plate to ridge height are 10 feet, We have less than that for our walls. So we have an 8-foot wall height and a 6.25-foot top plate to ridge height. So using the table in footnote 4, we can interpolate for our roof pitch. Again, remember we had a 5 and 12 roof pitch. So interpolating, we get a factor, an adjustment factor of 0.68. So multiplying that by the 12.3 feet that we pulled out of the table, we see that we have a required full height segment length of 8.4 feet. So if we go and look at our diagram, if we provide full height segments at the ends and between the windows, we're providing 13 feet of full height segments, which is greater than that 8.4, so we're all right. And again, this is with the assumption of that blocked gypsum on the interior. So there's a requirement in in footnote 2 of table 317D that states we do have a maximum aspect ratio of 3.5 to 1. However, footnote 2 requires that we block the gypsum wallboard where the aspect ratio exceeds 1.5 to 1. So for our examples, we do need to block the gypsum. So if you don't want to count the contribution of the gypsum, what if we don't want to have that gypsum, or if we don't want to block it, or for whatever reason we're not using the gypsum contribution on the interior? Well, we can go ahead into table 317D, and if you take a look at the table, the way it's laid out, this gray bar represents the exterior wall sheathing, and the white underneath it represents what the inside of the wall would be sheathed with. So for our wall, we're assuming we have a wood structural panel that's sheathing, and previously we had used this second row, this 1/2-inch gypsum wallboard, again, we needed to block it because of our aspect ratio. So if we aren't going to count the contribution of the gypsum, we would go to this first row under this heading where we have no sheathing or non-rated sheathing, and you see this sheathing type adjustment factor, this 1.3. So we're going to multiply that by our 8.4 feet, and we see that we need 10.9 feet if we're not counting the gypsum interior. So again, if we have our full height sheathing segments laid out as such, we're still exceeding that 10.9 feet, so we're okay. So our segmented shear wall would look like this, and again, we have to have hold downs on each individual segment. Now, what if we wanted to do a perforated shear wall approach? So for this approach, we assume that the entire wall is sheathed on one or both sides. So we have to go to table 317E, because one of the requirements is we need to have enough full height segments to qualify this wall as a perforated shear wall. So if we go into table 317, that helps us figure that out. So we have this big door opening right in the middle of the wall, that 6'8" door. So using our 8-foot wall and our door opening, we go back to that 8.4 feet of required full height sheathing that we had calculated with our segmented wall. So we've calculated that is divided by the full length of the wall, which means that 23% of the wall requires full height sheathing. So going and interpolating between 20 and 30%, we can get this perforated shear wall length increase factor of 1.86. So 1.86 times 8.4, that gives us 15.6 feet of required full height sheathing. That's with the blocked gypsum again. If we're not including the gypsum, we take that 10.9 feet value and divide it by 36, and that gives us 30%. So we don't need to interpolate that one. That's just going to be 1.72. So we get a required full height sheathing length of 18.7 feet without the gypsum. And again, remember our maximum aspect ratio is going to be 3.5 to 1 for our full height perforated shear wall segments. So we provided 21 feet of full height sheathing, and we only need to provide hold downs at the ends. So we've been able to reduce the number of hold downs in our wall by providing additional sheathing. So those hold downs, we need to go ahead and calculate the capacity requirements of the hold downs. And the wood frame construction manual prescriptive provisions, we calculate the hold down requirements for segmented and perforated shear walls the same way. It's based on the capacity of the shear wall panel, the first panel. So our hold downs for an 8-foot high wall would be 3,488 pounds. Now this is again for that baseline wall, but we do have a provision. We can use that sheathing type adjustment factor from table 317D and use it to adjust our hold down capacity. So for our wall without the gypsum, we divide that 3,488 by 1.3, and that gives us a load requirement of 2,683 pounds. So that's our requirement for our wall without the gypsum. Now this is just for the first floor. So if we were doing this as an actual design, we would need to combine this with the requirements from the top floor for the hold down requirements. And as I mentioned, these are based on the capacity of the first shear wall panel. So this is a little different than how we do it in SPDWS, and we'll talk about that when we get to that part of the program. But again, so this is based on the capacity of that first shear wall panel. And in the prescriptive provisions, we do not include any dead load offset. So that's the prescriptive approach. Now, if we want to get into the engineered approach, we go into Chapter 2. So Chapter 2 does have its own table of assumptions that you can take a look at here. Again, as I mentioned, one of the bigger ones for wind design is that we're allowed to do exposure D designs in Chapter 2 using the engineered approach. We don't have tabulated solutions for exposure D in Chapter 3, but we can accommodate those in Chapter 2. So the engineered requirements in Chapter 2 of the WFCM allow us to calculate the loads that were assumed in the prescriptive requirements in Chapter 3. So Table 2.5b of the WFCM shows the lateral diaphragm loads on the roof diaphragm and the floor, and the floor diaphragm. So we have a 5 and 12 roof pitch and a roof span of 30 feet. So we need to interpolate again. We're still in 130 mile per hour wind zone. So we interpolate here between that 87 and 101, and we get a roof load of 94 pounds per lineal foot. Our floor diaphragm loads are based on our wall heights, so half the tributary area of the second floor and half of the first floor. So using that, we calculate our floor load, which you'll see we've got several footnotes that are applied to both of these, but we're going to check footnote 2 here, and that is a height adjustment. So because again we only have 8-foot high walls and the tabulated values are for 10-foot high walls, we can adjust that value down. So we get our floor load is equal to 105 PLF. So the total value along the wall is 199 PLF. So we're going to multiply that by the width of the building, which is 30 feet, and then divide by 2, because we assume that half the load goes into each shear wall. So that gives us a resultant load of 2,985 pounds at the top of the first floor shear wall. So again, If we go into table 317D, right, we can see in here the unit shear capacity of our wall assembly. So we see that the wall where it has no sheathing or a non-rated sheathing, it has a capacity of 336 pounds per lineal foot. So that capacity is coming from that wood structural panel on the exterior of the wall. When we add the gypsum wallboard to the interior of the wall, we see that our capacity goes up to 436 pounds per lineal foot. So based on our required capacity of 2,985 pounds, you can do some math and figure out that the gypsum adds 100 PLF of capacity. So our wall that has the block gypsum on the interior has a capacity of 436 pounds per lineal foot. 2,985 pounds is the required capacity. So we can see that we need 6.8 feet of full height sheathing if we're using the capacity of the blocked gypsum on the inside. If we're neglecting the contribution of the gypsum, then we would need 8.9 feet. So again, using the segmented approach with the interior blocked gypsum, we see that we're able to accommodate our design with just the 2 panels at the end. So that 8 feet of full height panel is greater than the 6.8 feet that's required. If we're not using that interior gypsum contribution, we do need to add those smaller panels in between the windows. So we're assuming now that we're providing 13 feet of full height segment, which is greater than the 8.9 feet that's required. All right, so if we want to get into the engineered approach, but we want to do a perforated shear wall design, we need to make sure again that we have enough full height segments along the length of the wall. So L sub TOT, or L sub tot, is the total length of the wall between the hold downs. And then L sub I is our effective height of, or our effective full height sheathing, effective length of full height sheathing. Now with the perforated shear wall, we do have that adjustment on L sub I, and that's per SDPWS 4343. So that's this 2BS over H adjustment. We see that applied to our 2 small high aspect ratio segments between the windows. So that 2BS is 2.5, and then the H, the height, is 8 feet. So our effective length of full height sheathing becomes 19.1 feet. So our percentage of supplied full height sheathing in this case is 53%. So we go into table 4335 is the table here that's presented. This is from SDPWS. The same table is in the WFCM is table 317E in the prescriptive section. So what this does is it allows us to calculate our shear capacity adjustment factor, or C sub O factor. So using the table and for a full height sheathing percentage of 53%, we get a C sub O, an interpolated C sub O of 0.59. We multiply that 0.59 by the capacity of the wall. So for the wall with the block gypsum, our capacity is 436 pounds per foot. So we get a new capacity, an adjusted capacity of 257 pounds per foot. So based on the load of 2,985 pounds, our full height sheathing requirement is 11.6 feet. We're actually supplying 21 feet, or 19.1 feet of effective full height sheathing. So in both instances, we're greater than the required, so that's good. If we're again neglecting the contribution of the gypsum, we do the same calculation with a lower capacity wall, so 336 pounds per lineal foot times the C sub O gives us a capacity of 198 pounds per lineal foot. So we need 15.1 feet of full height sheathing without the contribution of the gypsum. So in both cases, our provided effective full height sheathing length of 19.1 is sufficient. So we need more full height sheathing in this perforated approach, but again, we have fewer hold downs. So, you know, it depends on who you're trying to make happy, your Simpson strong tie guy or your sheathing representative, right? So again, we need to calculate our hold down capacities. So once again, these are still based on the capacity of the first shear wall panel. So the values that you see here for the wall with the sheathing, that V is equal to 436 pounds per foot. So our required hold down capacity is 3,488 pounds, and that's the same as what we calculated using the prescriptive approach. And then for the wall with the gypsum being neglected, our hold down capacity, our required capacity is 2,688 pounds, which is, I think, about 4 or 5 pounds different than what we had calculated before. So there's a little bit of rounding, but it's essentially the same. Again, these are going to be based on the capacity of that first shear wall panel. So they're not based on the actual load. The wood frame construction manual has the hold down capacity requirements based on the capacity of that shear wall panel. You can account for dead load offset using the engineered approach, and there's language that allows for that in 2.24. And again, we need to combine it with the top floor hold down requirements so that would be cumulative down the height of the wall. So let's go ahead and jump into our next poll here. Marcy, take it away.
All righty. So let's see. The WFCM tabulated hold down capacity requirements are based on capacity of the first shear wall panel, do not account for dead load unless specified by designer, are cumulative with floors above or all of the above. So looks like everybody is right on top of things right now. So we've got about 50% have voted and 30 seconds. So I'm going to give you just a couple more seconds to get in there and vote. All right, I've got 70% have voted, so I'm going to close. And let's see, we've got a little bit of split between A and D. So 67% say all of the above, and 21% say are based on capacity of the first shear wall panel. Just a few between B and C. So, right. Lori, let's clear that up for folks.
All right, well, the majority is correct. Well, I guess technically you're all correct because it's all of the above. But again, yes, they are actually based on the capacity of the first shear wall panel. So you guys were listening, I emphasize that. We do not account for dead load, but you can. So if there are provisions, but the tabulated values do not account for dead load unless the designer is specifying it. And those hold down capacity requirements would be cumulative with the floors above. So the one that we just calculated was for the first floor. We would run that calculation again on the second floor and sum those values for the first floor hold down capacity requirement. All right, excellent though. Everybody's paying attention. Okay, so that was the wood frame construction manual. So now we're going to talk about the special design provisions for wind and seismic, or SDPWS, as I've been referring it to. So when you go into SDPWS in Chapter 4, Section 4.3, you'll see tabulated values for unit shear capacities for shear walls. And as you can see in the heading of this table, these are nominal unit shear capacities. So these values need to be adjusted depending on if you're doing an ASD or an LRFD design. We're going to do an ASD design today, so we're going to divide the values in the table by 2, and that'll give us our ASD capacity. So for our wood structural panel sheathing on the exterior of the structure, we're assuming we have a 7/16 thick inch panel, and our capacity is going to be 335 pounds per lineal foot. On the interior of the wall, we have a 1/2 inch gypsum board. Again, we need to divide the capacity by 2, so our contribution from that is going to be 100 pounds per lineal foot. We do have those higher aspect ratio segments between the windows, so I promised you guys that I was going to point out those the requirements on the shear wall aspect ratios more than once, and as promised, here they are again. So the walls where we have the aspect ratio exceeding 2 to 1, we need to multiply the shear values by 2bs over h, or sorry, the heights by 2bs over h. So we'll see that adjustment taken in our calculations. So again, we calculated our required capacity from the wood frame construction manual, so that 2,985 pounds. We're going to use that same value for our SPIDWIS design. We looked up our wood structural panel capacity and our gypsum capacity, and they sum to 435 PLF. We did use 436 as our value in the wood frame construction manual, so there is some slight rounding that has occurred. But when we divide the wall capacity by the required load, you see that our required height, or our required full height segment lengths are essentially the same as what we figured out earlier with the full height approach in the WFCM. So for the wall where we have the blocked gypsum on the interior providing a contribution, we have to have 6.9 feet of full height segments. So we can accomplish that with our 2 segments at each end, or 1 segment at each end, 2 segments total. So on the interior, or when there's no interior gypsum contribution, we do need to have that 2bs over h adjustment on the effective length. So that's that 0.625 value you see is equal to 2bs over h, where b sub s is the 2.5 foot dimension and h is that 8 foot height. So we apply that adjustment factor, and we see that we're providing 11.1 feet of full height segments based on our effective length. And that's still greater than that 8.9 feet that's required, so we're okay. Now, if we want to use the perforated shear wall approach in the special design divisions for wind and seismic, we can use the tabulated C sub O value. There are tables SPIDWIS that'll allow us to calculate that. Or we can actually calculate C sub O based on this equation. And what the benefit is for using the equation versus the tables is that the tables assume that all of our openings are the same size as our largest opening. When we use this approach with the calculated C sub O, we have this A sub O value, which is the total area of the openings in the shear wall. So we actually calculate the individual opening areas and account for them at their actual size. We don't just assume they're all the same size as the door opening. Our height is 8 feet. This L sub I, as we talked about, is the effective shear wall segments, the full height segments. L sub total is our total wall length between our hold downs. Again, A sub O is that total area of openings, and then R is the sheathing area ratio. So we calculate a C sub O, a C sub O of 0.77. So that gives us a pretty substantial increase in our allowable capacity of our shear wall. So by doing some more calculation, we are able to get some more capacity out of the wall. With the blocked gypsum, again, we had a capacity of 435 pounds per foot as an unadjusted value. So multiplied that by 0.77, we see that we need 8.9 feet of full height sheathing with a blocked gypsum interior. Without the contribution of the gypsum, we see we need 11.6 feet of full height sheathing. And in both cases, we're providing 19.1 feet of full height sheathing, so we're exceeding the requirements again. Now, for our hold down capacities in SPIDWS, these are a little bit different than in the WFCM. So we talked about how in the WFCM, the hold downs are based on that capacity of that first shear wall segment. With SPIDWS, we're actually going to base the hold down capacity on the induced unit shear. So it's based on the actual load. SPIDWS also has provisions in 43642 to account for dead load offset. And once again, you're going to need to combine these requirements for our hold down requirements with the top floor hold down requirements. So we see that the gypsum, with the wall with the gypsum contribution, has a hold down requirement of 2,985 pounds. And then the wall that does not include the contribution from the gypsum would have a hold down requirement of 1,840 pounds. Now, for the perforated shear wall approach, the hold down requirement is based not on the wall capacity, so it's going to be based on this equation 438. So it's based on the applied load, the C sub O, and the wall dimensions. So the hold down capacity for this is the same for the gypsum or no gypsum wall. So in this instance, it would be 1,624 pounds. Once again, you know, similarly, you'd need to combine it with the top floor hold down requirements. Like I said, again, it's based on the induced loads. It's not based on the capacity, so it's a different way of designing it. And again, we can account for dead load offset with the SPIDWS, with the engineered design. So here is a summary of what our designs look like for our three different approaches. You'll see the numbers in the square brackets represent the values for the wall with no gypsum, and the values in the parentheses, you see here, the 6 and 12, that represents the nail spacing. So for all of our walls, we were able to accommodate our loads with the same baseline design for our nail spacing, which is 6 inches at the edge and 12 inches in the field. So with that, I'm going to go ahead and give it over to Michelle, and she can shake things up with some seismic.
Okay, thanks, Lori. I had to unmute myself. Let's see. Okay, thanks everyone for joining us. And as Lori mentioned, I will be talking about a seismic example. And I'll go through the same process where we will go through the prescriptive, then the engineered, and then using the wood frame construction manual, and then the wind and seismic provisions. And let me make sure I'm engaging my screen here. And we will use the exact same structure that Lori used. Same openings, same overall aspect ratio, et cetera, et cetera. The difference is that we're going to be designing for a seismic load. And we'll be using a seismic design category D1. And then we'll need to know what additional loads are required in order to determine the seismic value or the seismic load. So we have a ground snow load of 30 pounds per square foot, a partial addict, and so with this partial addict, we're including the roof and the ceiling dead load, which is 25 pounds per square foot. And then we have a floor dead load of 12 pounds per square foot, a partition load of 8 pounds per square foot, and then a wall per linear foot load of 110 pounds per square foot. And similarly, we'll be looking at the first story shear walls. So the added loading that comes down from the roof all the way down through that second floor and being applied at that top plate at the first floor, top of the shear wall. And so right off the bat, we'll start off with the prescriptive design. And as mentioned previously, we have seismic design category A through D. We have segmented and perforated shear walls and some other applications. But one thing I want to mention is Lori, she presented for about an hour, and I'm going to be presenting for a little less than a half hour in order to provide some time for Q&A. So I'll go through the same design example with the seismic load and point out the differences between where it's specific to seismic design. Now, you've been provided with a full design example similar to what was done in the wind, but I'm going to skip over the areas where the process is the same. You're just doing it with a seismic load, but we wanted to provide that complete design example for you so you have it in your notes. So in other words, I'm going to be fast forwarding through some part of this presentation. And I wanted to keep the slides in this presentation so that if you had to refer to a slide number, you would have, it would be sequential to what you have in your notes. Okay, so one thing I wanted to point out, and I know Lori mentioned this previously, but I want to reiterate it again, is that in the wood frame construction manual, we cover seismic design category A, B, C, and D. But D, some of you who aren't familiar with the IRC, D is a subcategory with D0, D1, D2 in the IRC. So the IRC breaks it down even further so that it can fine-tune the seismic design when it looks at the residential design of a building. And this makes sense when you think about it. For example, if you're designing for track housing, you're designing for one building, but that's used multiple times within a track, you really want to fine-tune your calculations and reduce some of the cost on that one design that could be used multiple times. So that's one reason. So where we're going to go with our design is seismic design category D1. And then also when we do our design, we want to make sure we meet the minimum, the descriptive, prescriptive design limitations. These are simplifying assumptions that are made to create the wood frame construction manual, to have a baseline for what we're developing the document for. Now, when we talk about the baseline assumptions, this is one of them related to the construction of the actual shear wall. In the seismic, if we're designing for seismic loads, it's similar to wind loads in that the makeup of our wall has minimum studs at 16 inches on center, 3/8 inch wood structural panel on the exterior of the building, and then 8-penny common nails, 6 inches on center on the panel edges and 12 inches on center in the field. Now, different from wind also included a minimum requirement of having gypsum on the interior face of that shear wall, whereas we do not have that for seismic. We don't take into account that additional capacity, whatever that may be, in our seismic design. So again, the minimum is 16 inches on center stud spacing, 3/8 inch wood structural panel, 8 penny common nails at 6 inches on center and 12 inches on center on the field. Now, on the previous webinar that we did, we got some questions about what does it mean by 6 inches on center panel edges and 12 inches on center field nailing. So the 6 inches on center on the panel edges is just that, all around whatever wood structural panel, that panel edge, we're going to have some nailing of 6 inches on center. So it's at the top plates, it's at the sill or sole plates, and it's at the side panel edges wherever it meets the framing member. Whereas the 12 inches on center field is intermediate to the intermediate studs, or if you're talking about floor joists, it's at the intermediate joists. Okay, so that's our minimum requirement for a construction of our wall at the exterior. And now what we look at in the prescriptive design, we're going to find out what are minimum requirements of the length of the shear walls that is needed for this load that is being applied to the building. So we have table 317C1 for our segmented shear walls. We start off with segmented. Even if we're only going to do perforated, we always have to start off with our segmented shear wall design. This table is for seismic specific, and it has a ground snow load of 30 pounds per square foot. Now, we also have tables that are 50 pounds per square foot and 70 pounds per square foot. And then also within these tables, we have all the way, this one just shows the roof, ceiling, and one floor. So we're designing this lower level, which could be equal to the upper level for the lateral design. We also have one that shows the 3 stories. So there's various versions. This is a truncated version of the table. And we have seismic design category D0 and D1, and there's also a D2. And we know from previous discussion that we have our width of our building is 30 feet, and then our aspect ratio of our building is 1.2. So we're going to have to do a double linear interpolation here to come up with our length of the shear wall that we need. And that is, through the linear interpolation, is 15.8 feet. So that's the required length of full height sheeting. So then we go, are we good to go? But wait, there's more. Anyway, so a little chuckle there. Dead load assumptions. We had 15 pounds per square foot for this table. Well, when we looked at the criteria, we actually have 25 pounds per square foot. So in the footnote of this table, footnotes to table 317C, it states in footnote 4 that the sheathing lengths can be determined for other dead load cases by multiplying the length by an adjustment factor. So this is a handy table if you have something other than the baseline that we showed previously. So, and this is a good thing to look at here also, in that the baseline is 15 for the tables, and then we have 12, 8, and 110 pounds per linear foot for the wall. So an adjustment factor for that would be 1.0. So that's a cue there that that's our baseline makeup of our building. Something other than that, then we've got to adjust our length by this length adjustment factor. And in our case, we're at 25 pounds per square feet. And then we have 12, 8, and 110. Our width of our building is 30 feet. And so we come over and do this linear interpolation, which really isn't linear because it's both 1.2. And so 1.2 times our previous number of 15.8 gives us 19 feet. So that makes sense. We had the design or the prescriptive length of the shear wall is 15.8 feet, but we have more weight. So that means our demand on our building is going to be more, and we're going to need to have more length to our shear wall. So a 20% increase in our length. So our required length of our full height sheathing is 19 feet. Now we go to the same table that Lori looked at, but which is 317D, but we're looking at the seismic requirements, not the wind. And we have a sheathing type adjustment factor. going back to just the overall general look at the table, the exterior is always going to be in gray. So whatever's in the exterior is going to be gray here, which is 3/8 inch wood structural panel, maximum stud spacing at 16 inches on center, 8 common nails at 6 inches edge spacing. Now, whatever's on the interior is in the white. That's all in white. So if we want to add something, that's in the white. But if you recall, so here we go, here's the sheathing type adjustment factor, and this is the column for seismic. Let me see if that, let me go here. There we go, seismic. And you can see that if you recall in the beginning when I talked about the minimum construction of our wall, we do not take into account the gypsum on the inside of the wall. So that's why first row is 1. That means there's no adjustment. We didn't have any gypsum. Second row is 1 as well, because although we've added 1 for interior of our wall, we're not taking that into account when we do our seismic design. And then if we wanted to have wood structural panel, we have a different coefficient. But right now, we're just going to start off with the baseline, just the baseline construction, and go from there. Now, the other thing had to do with this column here for seismic design. Our maximum aspect ratio of our shear wall is 2:1. If we go greater than that, we can go up to 3.5 to 1, but we have to reduce our, we have to take into account the stiffness of the shear walls. And Lori went over this, and this is the stiffness adjustment. And Lori mentioned it was from this part in the wind and seismic provisions, taking into account the various stiffnesses or what can happen when we have bigger aspect ratios than 2:1. So here we go. Here's the design. We have the same shear walls that Lori did, 4 full height shear walls at 4 feet, and then 2 full height shear walls at 2.5. So the actual length of the shear walls is 21 feet. And because the 2.5 shear wall doesn't meet the aspect ratio of 2:1, we've got to take into account that stiffness factor. And so we have an effective length of 19.1, which exceeds our required length. So we're good to go. And then similarly, we'll have to have shear hold downs at each end of those full height segments. Now, from here on out, the process is the same as what Lori went through. So I'm going to skip through this, knowing that it's the same process, and that although we're dealing with seismic loads, so there's no difference between the process. The one thing I want to reiterate about these sheathing adjustments for perforated shear walls, these tables are based on the largest size opening. And then there is some calculations that we can utilize to actually take into account the smaller openings and not just penalize the entire wall based on the full size opening happening everywhere where there's an opening. So I'm going to skip through and go to the results. When we go to a perforated shear wall, we are now, our nails, sorry about that, are at 3 inches on center edge nailing, 12 inches panel field nailing, where before on the segmented, we had 6 and 12, but we also reduce our required hold downs to just 2, and as opposed to 1 on each side of the full height segment of the segmented. The hold downs are calculated exactly the same based on the capacity of the shear wall, as Lori mentioned. And no dead load is taken into account when analyzing this capacity of the hold downs. Okay, so Marcy, we have our, what is it, the 4th poll?
Indeed. So WFCM seismic tabulated shear wall values assume which of the following? So is it studs are spaced at 24 inches on center maximum, 19 32nd of 1-inch wood structural panels on the exterior, 8-penny common nails at 6-inch on center panel edges, or 1/2-inch gypsum wallboard capacity. And which of those is it? So we've got about 45% have voted in 30 seconds, so just a few more seconds. I know I'm going faster on the polls than usual, but we've got a lot of information to cover, so I'm going to close it. And let's see, so 75% say 8-penny common nails at 6-inch on center panel edges. Is that right? So, all right. So, and just a few on the others. So go ahead, Michelle, and let us know how that went.
All right, thank you. Sounds like about 70-something% was paying attention, and my repeating that a few times helped. So yes, that's correct. We have studs at 16 inches on center max, not 24. We have 3/8-inch wood structural panel on the exterior, not 19/32. And then on the gypsum wallboard, we do not include that when we're doing our seismic design. Those are the simplified assumptions that we're using when we're designing these or determining the prescriptive design. Okay, now we're on to the wood frame construction manual, the engineered approach. And this is where you obviously need to check the minimum requirements in the table 2 that are in the beginning of chapter 2. And also what we're going to do now is, instead of saying this is the minimum requirement length that we have, we're going to look at it from a different standpoint and saying, what's the induced loads on this structure and what's being applied to this structure, and then determining what we need for our structure. So this table is table 2.6, which provides a method for determining the actual lateral loads. The top table is used to determine the shear at each level, which is shown here. And we're looking at a 2-story, so we're going to be using this equation for our loads. And then the bottom part of this table has to do with determining or calculating the shear at each level for the shear capacity requirements of shear walls and connections. And you can see this equation right here is may be a familiar equation to some of you who use this approach from ASCE 710, which is a simplified approach for determining the seismic loads for a building. There are some minimum and maximum requirements to use this approach, which the wood frame construction manual fits nicely into. And the requirements here are, or our S sub ds for the D1 is equal to 0.83. Then we have a response modification coefficient of 6.5. Our vertical force distribution factor is 1.1. These are plugged into the equation along with the weight to determine our seismic load. Now this 0.7, even though it's not part of the equation, it's just there to remind people that we are using an ASD design and not an LRFD design, and these equations incorporate this for an ASD design. So we've determined, maybe we could spell that out in the future, but our total weight of our building that would contribute to the seismic load is 83,680 pounds. We plug all our coefficients into the equation, the 1.1, and then here's our dead load of our building, and then 0.83 divided by 6.5, we get 8,228 shear load at the second floor level that will be applied to the first floor shear wall. Now, just to give you some background on this simplified approach, it's this page 28 in the wood frame construction manual commentary provides you some step-by-step detailed information on the lateral design that's used in the wood frame construction manual, just to demystify any thought that there might be, we're pulling these numbers out of a black box or something, just to open that up and say, this is where we've determined the design methodologies that are in the wood frame construction manual. It's based on the simplified approach, or it is a simplified approach. And this is just a blow up to show you where the equation comes from, straight from ASC 712.14.8, which states that V sub RD, and this is just for the roof diaphragm, is equal to 1.1. That's the vertical force distribution factor for two-story. And then the S sub DS, and then, well, the weight, and then the S sub DS, and then divided by your seismic response modification coefficient. So if you want more information, it's in the commentary. Now, similarly to what Lori did, we use the same table, but again, we're only looking at the seismic portion of the building or the table. And now, instead of looking at reducing or modifying the length, we're actually going to look at it from a capacity side. So the capacity of the shear wall is 239 pounds per linear foot for the baseline shear wall. And again, you can see it's the same. We don't take into account the drywall on the inside of the building or the structure. So we want to know what capacity, we know the capacity, and we want to know what length we need based on that capacity. So we take our total lateral load of 8,228, assume that we have a flexible diaphragm, and divide it by 2 to get it to each line of resistance, and then we have 4,114. And as mentioned from the table, our capacity of our shear wall is 239 pounds per linear foot. And you have the demand of 4,114 divided by the capacity of the shear wall, which is 239, and we need 17.2 feet of shear wall with this capacity, full height shear wall. So we go, okay, since some of these shear walls don't meet the aspect ratio, what's our effective length of those shear walls, given that stiffness factor? So that's where we come in. Our actual length was 21. We have a effective length, taking into account the stiffness of the shear walls, the shorter walls that don't meet the 2-to-1 ratio, and we come up with 19.1. So our effective length is greater than our required length. And then, then we go on and do our perforated shear wall design. And then as same procedure, just different numbers. So I'm not going to go through this in detail. Just mention again that these tables are based on the largest opening, but there is a methodology where you can take into account the smaller openings. The other thing I want to mention about this table here, table 317, is when we're combining a wood structural panel and a gypsum for the wind design, we don't combine the two as if it's an additive method. We take into account where it says in the wind and seismic provision 4.3.3.3.2, where you take the larger of the one capacity or take the lesser of and then multiply it times 2. So we use that as a guideline to come up with these factors that are shown here. It's just not something pulled out of the hat. It's based on the wind and seismic provisions. Okay, so I'm going to skip forward through this because Lori did the same process earlier, and just go with the summation of our effective full height shear wall was 19.1, and our required for the perforated is 15.5. So we're good to go. Overturning hold downs are the same, similar to what Lori did. And the one thing I want to point out is this is based on the applied load. In the wood frame construction manual, it's based on the actual capacity of the shear wall. Now, the dead load can be used, or at least 60% of the dead load can be used for resisting that uplift, but that's only for the engineered approach. And that is mentioned in, let's see, I think it's 2.2.4, where it mentions that 60% of the dead load may be used. So that's in the engineered portion of the table. Now, we have one more poll, Marcy.
All right, here's the last one. The tabulated perforated shear wall shear capacity adjustment factor is not based on the maximum unrestrained opening height. Is that true or false? So it is not based on the maximum unrestrained opening height.
Is it based on it, Marcy? Not? It's not based.
I'm just stressing that.
Very good.
All right. So I've got about 60%. I'm going to go ahead and close. All right, so 71% said false, 29% said true. So let's find out how that really is.
Very good, Marcy. I think your emphasis on not helped a lot. Thank you. Okay, that's true. It was a tricky question, but we know how smart our audience is, and they caught that not based on the maximum unrestrained opening, because it is. Okay, thank you. Now we'll go through the, I'm going to skip forward because Lori actually did much of this. The only thing I'm going to point out is that the wood frame construction manual, as she mentioned, does not take into the aspect ratio reduction for stiffness when designing for wind. It does, and it does not do it for it does do it for seismic, and but not wind. In the 2018, it will. So I'm going to skip forward. It looks at stiffness, it looks at strength, and then takes the worst case scenario where the stiffness governs, and we come up with some full height shear wall requirements. The wind and seismic provision does have some efficiencies in its design, or the complete design, more fine tuning of that pencil, to come up with a more efficient structure or shear wall system. I'll go forward, and we'll go through and get the actual summation. So here's the summation of just the seismic design. As you can see, because of the simplified assumptions, that the prescriptive approach is going to be more conservative, and you can see that looking just even at segmented, we're seeing some efficiencies in an engineered approach through the wood frame construction manual. The perforated shear wall, although there's less shear wall requirements, we have more nailing requirements and more hold down requirement for the perforated shear wall. But those are only 2 hold downs as opposed to 1 at each full height shear wall. Then the wind and seismic provisions should be very close to what we see in the engineered wood frame construction manual, which you can see here, very close. This one is exactly, and the perforated is off a little bit. But we also have some efficiencies in our hold down because we're really fine tuning that design of this. And then as a side-by-side approach from the wind to the seismic, you're going to see a difference, obviously, because we have different demands on our structure. You have a wind load, and then you have a seismic load. And obviously, depending on what part of the country, one would govern over the other, but we still have to check both, or we're required. Some ways, like in Southern California, even though it's high seismic, depending on the configuration of the structure, wind could govern in some cases. So looking at this, we see that for wind design, it's, again, we don't have that aspect ratio adjustment in the wind design in the wood frame construction manual, but you're going to see some changes in that in the 2018, where it's probably going to get closer, may get closer to what you would see for the seismic. And then this is just side by side, more demand on for seismic in some areas. Okay, I think that about does it. We have our wood frame construction manual. Our wind and seismic provisions are available on our website, free download, except for the commentary. We also have the 2018 that's available. And you should note that the wood frame construction manual and the NDS were updated in the 2018 edition, but we did not do any updates to the wind and seismic provision. So if you're under the 2018 IBC, it'll be the 2018 wood frame construction manual with 2018 NDS, and then the 2015 wind and seismic provisions. There's some other resources that are available as well to help you with your design that are noted here.
I've had some questions come in, so Lori, I'm going to have you take this first one, which has to do with hold downs at the corners. And we showed a detail there. Can you talk a little bit about whether we require one or two hold downs at the corners and how we handle the shear between those walls? And you might be muted. Yep, you're muted if you're trying to talk. There we go.
Thank you. I was muted. So we have this illustration here on the bottom left corner of this slide here that shows our hold down. So the short answer is yes, you can use one hold down at the corner, but you will need to ensure that you have that corner stud there connected to transfer the shear to the hold down. Obviously, if you have two different walls, they'll have two different hold down requirements. So you would need to ensure that the shear for whichever wall does not have the hold down directly attached to it. So in this case, it would be this portion that detailing needs to accommodate however much shear needs to be transferred to the hold down.
Great, great. So you calculate both walls and take whichever one controls, and then you can use one hold down as long as you can get the shear around the corner. Excellent.
Yes.
Michelle, related to that, we never, or maybe we did, but let's talk a little bit more about dead load assumptions for hold downs and what's permitted and what we assume in the wood frame construction manual.
Okay, so good question. I did mention something, but I didn't expand on that. The wood frame construction manual, the prescriptive approach does not assume, you're not assuming any dead load to resist that uplift, just because there's so many variations in the layout of the building. For the engineered approach, we're allowed to use 60% of the dead load to resist any uplift for that hold down. And then in the wind and seismic provisions, there's no criteria really for the amount of dead load. It's an engineer's judgment on what they choose to use for the design of the uplift and the resistance by dead load.
And if you could also, either of you, I guess, distinguish between uplift at a hold down versus wind uplift on a building and how those are resisted and what assumptions we make on dead load in the wood frame construction manual. So
the hold down is going to resist your overturning forces. The anchor bolts that would be along the length of the wall, those are going to be there to resist your in-plane uplift, like along the length of the wall. And what was the second part of that question, buddy? Sorry.
No, that's okay. So what do we assume in the wood frame construction manual as far as dead load offsetting one or the other of those?
I think Michelle briefly alluded to that. So for the hold downs in the prescriptive approach, both wind or seismic, we don't have any dead load offset. There are provisions in the engineered approach for the hold downs to have dead load, a portion of the dead load used to offset some of that uplift. And then for SPDWS, again, you're allowed to have some of that overturning force resisted by the dead load for the hold down. And I do believe that, buddy, correct me if I'm wrong, the uplift forces for the anchor bolts, the tabulated values, do have a portion of dead load assumed based on the wall dead load.
Correct.
That's specified in, I think it's specified in C112 in the commentary.
Yeah, yeah. So we do assume both roof and wall, and I believe maybe even a portion of the floor dead loads are going to offset those straight wind uplift loads. So it gets a little confusing for some folks who are used to calling uplift on a hold down in seismic territory. When we call uplift for wind that we're dealing with for anchor bolts. Did you have something else, Michelle? Go ahead.
I was going to mention the new anchor bolt tables that we have for uplift that came in the 2015.
Oh, yeah. So we didn't cover that today, but the wood frame construction manual allows the use of wood structural panel sheathing to resist both shear and uplift. And so instead of straps at all of your studs that might be used instead of anchor bolts into the foundation, you can use the wood structural panels, and then the anchor bolts could carry the loads into the foundation, and that would also apply between floors. So good point. There were a couple of questions about the load assumptions and whether we're assuming ultimate or allowable stress design loads. I can take that if you want, or if one of you want to address that question.
Well, the wood frame construction manual is all allowable stress design. Is that what the question is?
Yes, that's correct.
Okay. In the wind and seismic, you could do either.
Correct.
It's for both.
Yeah. And in the wood frame construction manual, if you go to the commentary, we keep referring to that a lot, it shows the 0.6 adjustment factor to go from the 700-year return ultimate loads to ASD loads that are then used in the wood frame construction manual. All right, let me take a look here. So maybe reiterate one more time where we're allowed to use dissimilar materials, the shear wall capacity for dissimilar materials, say wood structural panels on one side, gypsum on the other.
So I have this section if you want. Or
yeah, you want to
go
take
ahead.
the
No, you tag your it. No.
Okay. I don't think I have the reference up on the screen, but if you go into SPDWS in section 43332, there's an exception, and let me get it out here. So the exception states when you have wind-controlled design, the unit shear capacity of shear walls sheathed with a combination of wood structural panels on one side and gypsum wallboard on the other side, you can sum the sheathing capacities on each side. So that's something that I've seen a lot of heads being scratched from our friends on the West Coast who aren't used to that provision. So that's for wind-controlled designs only. So if you're in a seismic region or a seismic-controlled design, you would not be able to sum the capacities of the dissimilar materials. But for wind designs, which is the first set of examples that I ran through, we do have that provision that allows us to sum the capacities if we have wood structural panel on the outside and gypsum on the inside. Okay. Otherwise, if it's the same material on both sides, you're allowed to sum those. But for the dissimilar materials, it's only wind-controlled design.
Okay. So we've talked about hold downs being required pretty much for all of these designs. Can either of you address the where the IRC, the International Residential Code, could be used, I guess, or where does the wood frame construction manual kick in as a required methodology versus using, say, the braced wall provisions of the IRC?
I don't have the number off the top of my head, but I believe that the IRC limits your wind speeds to, was it 110 miles per hour in the braced wall provisions?
Yeah, I know there's a map.
There is, yeah.
That shows where hurricane design is required. And so if you're in that shaded region, then that kicks you out of the braced wall provisions into something else. And something else can be the wood frame construction manual if it's wood frame construction.
Absolutely.
Okay.
And are there any, I'm not aware if any seismic provisions. Michelle might be more on the up and up with those.
Yeah, I can't remember what the seismic triggers are, but they probably above seismic C, so maybe A, B, and C or something like that. Would be you'd be able to use the IRC brace wall provisions, but check the IRC to see where that happens. All right, one more about screws used for gypsum wallboard versus nails. Are screws permitted, and are there capacities, shear wall capacities for those?
So screws are they are permitted. There are provisions in the wood frame construction manual and in the special design provisions for wind and seismic that allow alternate materials. They would need to. The caveat to that is we don't have tabulated values for those. So you would need to go to either the screw manufacturer or an evaluation service report from a third party that provides the shear design values for those that assembly, the screws and the gypsum. So you can use them in conjunction with our standards, but you'll need to get the design info from somewhere else.
Let me qualify that, because I took this question behind the scenes while you guys were teaching. I went to table 4.3c of the wind and seismic standard, and there are a couple of entries here for drywall screws.
Oh, okay.
For the SPIDWIS, you can get some capacities for these screws, and if you look at them and see that they're comparable or above with the capacities that we assume in the wood frame construction manual, then you could potentially use those values per the wood frame construction manual as well.
But other than that, Lori mentioned if they're not covered in this, then they would go to ISANTA.
And in the other webinar that we had today, there was a question about using screws in wood structural panel diaphragms, and we do not tabulate that in SPIDWIS. So you'd need to go to an alternate source like ISANTA or APA for that information.
Okay, I think we're up on the
time. We're about 5 minutes past, so why don't we wrap up today. Thank you both for an excellent presentation today, and thank you everyone for being here, and we hope to see you next month again for our next webinar.
Thank you, everyone.
Thanks a lot.